have the ball. Let me see. It's a way to. What? I transfer that before. All right. Grab URL for everyone, and there's that. All right, so we have our in-memory representation. So let's go for a second graph to start. 2, 4. In fact, let's just go steal. From the previous. And create the matrices that way. And some labels might help. Maybe C and G, and then just using the letters of the alphabet. For no particular rhyme or reason. Same choice, but the same again. Right, so you may recall alphabetical order for the vertices. Okay, A going to each of its neighbors, B is going to each of its neighbors, and C is going to each of its neighbors. Pretty small graph. Right, and we'll see that this one will line up with a complete graph because every vertex is connecting to every vertex that it can connect to. And that's just a small edge case, get larger. That will no longer hold true. All right, A connects to B, B connects to C, C connects to D, and then we'll have the mirror of that. And am I forgetting? Where's my back? C goes there. C goes there. And so every single row has 2 turned on. Right, so if it's left blank, blank just means 0. Easier to see the patterns. Not all the positions are filled up, so leave it like that.
Excuse me, Professor, is there a way to boost your mic? It's a little difficult to hear.
Yeah, let me double check what. Did I change anything?
It's a little bit better, thank you.
Enough to do inside Canvas for my audio options. I don't see anything here. Oh, just remember also speak louder. Okay. Up to our C5 graph. Again, labeling in alphabetical order, numeric order. The labels are numbers, whatever it is. A goes to B, B goes to C, C goes to D, D to E, and E goes back to A, and we have the mirror. And it's like before, 2, 2, 2 across the board for each row, or if you want to get by column, same story. It is a simple graph. Right, so if I give it to you in the reverse, if I give you a matrix or a list, we can draw the graph from that, which doesn't work too well, generally speaking, on a computer-based test, but I can give you, right, ask you, what shape or shapes does this graph fall under, right? everyone's 2, so it's a cycle graph, and because it's a C3, also a complete graph. Keep that in mind. All right, next up we have our star graphs. And we'll start with S4. And we'll test some labels in here. Just have A be the center spoke. Line up. All right, so A being the center spoke is going to be fully connected. Let's turn on. And we're good to go. Right? B goes to A, C goes to A, D goes to A, and A goes to everyone but itself. And the pattern will just be the same as we get larger. Right, and we just added another perimeter vertex with E, basically the same graph. One extra entry, right? So star graphs are fairly disconnected graph shape. Just go ahead and grab the whole thing, paste, and add in for F. All right, and A connects to F, and F connects to A. Questions open. How are we doing with these memory organizations? Are we doing good enough to build these on our own, or should we just rip through them all? You know, what we can do, we'll toggle over to adjacency lists. How about that? For our next ones. And we'll keep A in the middle. And let's do A this time. We have B in the middle. And we'll see in the middle this time. Just keep things a little bit different. Two B's, so there are. Thank you. A, B, C, and jump to E, number D. Screenshot. Work off on the side here. All right, let's get drawing. In fact, let's see. No, nothing still from there. Fresh. All right, first up, we'll have our array. Represent our origin vertices, right? We have 4 vertices, so 4 elements in our array. And W4. A, B, C, and D labeling those elements. And we'll just see who they connect to. All right, so A chopped off here. Next, everybody. connects to B, connects to C, connects to D. And so we'll have B, C, and D in its adjacency list. B, C, and D. And with our smallest wheel graph, we're going to have that same pattern here, where it is a wheel and also can be construed as a complete graph, because everyone is connecting to everyone else. Get my labels here, all good. Right, for a K4, right, for the reducible to K4, right, complete graph, 4 vertices, that means the degree, every vertex is going to be equal to 3. Just like we have here with our wheel graphs. So a little bit of overlap in state with small ones. When they start getting bigger, and that tends to cease being the case. We'll go up for F5, W5 that is. The array needs to get bigger to account for E, and then all my labeling is quite wrong here, so I'm going to go a screenshot, see who's pointing to who. Okay, A connects to B, C, and E. So we need to fix this, C, and E. We have B, B goes back to A, goes to C, goes to D. A, C, and D. And I happen to be the same here, so that's good. C, next to everyone. This list is going to be longer, so A, B, C, D, and E. That's the on there. D, D goes to B, C, and E. Updated E, C, and E. And then lastly, E goes to A, C, and D. A, C, and D. So once we get to this point, we break with complete graph. Degree of every vertex is 3, with the exception of our central spoke. Central spoke is going to connect to everyone else. Grab an image, 6, same pattern, just growing a little bit bigger. All right, colors back, and colors that, almost. All right, so this time we'll have D as the center, so it'll have the most connectivity. And we're adding F into the picture. Right, so just like 4, we're going to have 3 on for everyone. That is not middle spoke. Go ahead and clear this all out. Type in what it's going to be on how the graph is drawn. All right, so let's check out the graph, see where A fits, see who it's connected to, right? CDF, CD and F, and same story for everybody else. C, D, E, and G also in alphabetical order. C goes to ABD. Right, because you gotta remember this particular graph can be drawn in lots of different ways. The alphabetical is the only way to have consistency. Right, D. Except everyone else, A, B, C, E, and F. And then E, we have B, D, F. And lastly, F with A, D, and E. All right, so that's your key indicator if you're just looking at matrix of graphs for a wheel is to see a degree of 3 for everyone except whoever might be the center spoke, which if we're just looking at this list, it's impossible to know who is our central spoke for a W4. Any of them could be the center. It's all degree 3, but can't tell. Once we get to W5 and beyond, whoever has the most connectivity is our central spoke, and then everyone else is on the perimeter, connecting it to their two neighbors and the center. You'll find C listed in all of the perimeters. I mean, all the lists for our perimeter vertices. All right, who we have? Complete graph. Assuming everyone's doing good, no questions flying. Okay. I wasn't frozen. I was just pausing for questions and stealing a bite of dinner. But everyone, lots of people paying attention because I apparently was apparently not moving, so that's good. All right, let's do the list. List, matrix, any preference for our complete graph? Matrix, all right. How about we go back and forth? So we'll do the K1 in the matrix. It'll be quite the small. So we need some lettering in here. Call this one A, C, D, E, F, G, H, I, J, and so on and so forth. K, L, N, and an O. We have RK1, which is a little bit ridiculous, but it is as connected as it can be, which is to no one. Okay, A is quite the empty graph. Our K2. All right, so we have 2 entries in our list, and then we'll have 1 entry in each of those lists. We had B and C. Here's our labels for vertices. So B connects to C and C connects to D. All right, toggle back over to our matrix. And K3. We want to go D, E, and F, D, E, and F, D, E, and F. Right, D connects to everyone that it can connect to. E connects to everyone that it can connect to, and F connects to everyone it can connect to. And the diagonal is 0. Our K4 and W4 as mentioned previously. And let me cheat here and relabel here. A, B, C, D, and E, and that way my answer is already done. A, B, C, and D. All right, so all you gotta do is change my W4 list to a K4 list. It's nothing. I will change my labeling here, right? A connects everyone that it can connect to, just A, B, C, D. Same story for B, same story for C, and same story for D. Connects to everyone that it can connect to. All right, so we have for K5. Take a previous matrix and some. And do you need to fix our lettering here? Old screen. See what we can get. All right, KLMNO. Okay, M and O, and again, and where am I alphabet here? All right, so K connects to everyone. Same story for L, M, and O. So I'll just put zeros down the diagonal, and we'll turn on everything else. And numbering. And there's our K5. Last will be a complete bipartite. Just regular bipartite graphs are going to fall into the general category of graphs. Once they become complete, then it's a little more interesting pattern inside lists and matrices. Okay, let's see. So these 1, 2, 3, 4. Yeah, 5, not 6, 7, 8. And fill out matrix, right? So 3 vertices, our matrix needs to be 3 by 3. Like that's the K1, 2 is not changing anything. We have vertex 1, 2, and 3. 1, 2, and 3. And connect 2 and 3. Excuse me. 2 connects to 1, 3 connects to 1. And getting larger with our K2, 3. 5 vertices. We need 5 by 5. 5, 7, and 8. All right, so set A has 4 and 5. Connecting 6, 7, 8, and 6, 7, 8. And on the flip side, we have these two 4 and 5 connecting to 6, 7, and 8. Actually, you'll get nice little regions when you look. Let's see. Border borders. Two. I can get colors the way I want. Color. All right, let's go back on colors. Here's a grouping and similar grouping. Right, so no cross listing. You look at the rows or the columns for the other sets of vertices. Any questions about matrices or this? Is there a programming question? Is there a question is there a programming advantage to knowing the shape? Not that I can think of off the top of my head, but certain situations will call for various shapes. Right. And for example, like the internet. Let's see if we can find my image I want. Not finding what I want just yet. I'll find it in a second. That's what I want. Right. So the internet. If we zoom in here. And working. Right, the internet is a composition of star graphs. So you can see we have some. There we go. Right, like in this area here. Where is my annotation? There we go. Right, in this little subnet here, network, a whole bunch of computers connected to Centerpoint. Yeah, this was probably a long time ago. It was generated, but this was just basically a crawler crawling the internet, and then basically mapping out the IPv4 network schemes to see who's connecting to who and all that fun stuff. So like your home network, you have your router. That router connects to your cable modem, or might be the same device, and all of your devices connect to that one. So that single point goes down, and your whole access to the internet down, right? Your network may well still be up. And if your router stays up, but your cable modem goes down, so you can communicate within your network, but then you're blocked from the outside world. And the vast majority of the internet is based off of that particular pattern. It's a bunch of stars together, but then, you know, we don't want, if we have a larger central point go down, right, the fiber connection into the university goes down, right? Well, the entire university network can go down with it. There's a little bit of redundancy in the network, right? There's multiple domain names, there's multiple ways to get from one point to another. So, but there's still stars, layers of stars on top of each other for the most part. The Wikipedia entry of the internet. Pop that down. Right, so in networking, that same problem used to happen where computers were actually daisy chained together when, a little bit before my time still, but you had coaxial connections, and you'd have like a cable, like your TV cable, connect a computer, and then the next computer down the line connected to the computer in front of it. And their wires were just physically tapped into each other, so connection itself was spotty. And if a computer further up the chain goes down, then you go down as well. So there's more room for failures. So the first solution they came up with that was to do a cycle-based network. So the last computer connects back to the first computer, and then wherever the connection is to the outgoing network. So if one computer goes down, there's an alternate route to get back and still be online. And so failure is always an option in computing systems. Something's always failing somewhere, and we need to try to account for it as best we can. The database might go down, the internet might go down, the network might go down, packets can be lost, timeouts hit because the system is overloaded. Always going to have failure all over the place. For the matching problems, that's where our bipartite, complete bipartite graphs are relevant. So in that case, you do need to know the shape of the graph because that's the requirements of the algorithm to have a graph of that particular shape. So if the data is trying to say it's something else, the code can validate that, no, you can't have this edge in the graph because it violates the rules of the shape. Okay, next up we have is traversing. Traversal, okay, search. Yeah, so in that internet diagram, those really dense apartment complexes probably wouldn't have been relevant at the time because that graph's quite old and not many apartment complexes offered internet at the time. So those have been universities, government institutions, right? Places that were, universities were among the first to be internet enabled on a broad scale. Back with, oh man, ISDN connections and things like that. That was the big pipe way back in the day. Compared to your 28.8 or your 14.4 kilobit modem, getting 768 kilobits was amazing. Until you're sharing it with 1,000 people, then it's really slow. Let's see. All right, traversals. All right, so our graphs are typically going to be non-linear. So if we want to iterate across the entire structure or search for another vertex in that structure, we'll have to take a non-linear approach. We have two ways to go about this: depth first search and a breadth first search. And so depth first search, order. With this approach, you go to the first neighbor of the starting vertex. Then from that vertex, go to its first neighbor. What we don't already know about. And we repeat this pattern until we get to a vertex that has no unknown neighbors, at which point we'll backtrack to the previous vertex. And this will go on until all vertices are hit, or the vertex we're looking for has been encountered. All right, so let's go ahead and create a graph. Create some nodes here, and we'll link them up, and then arbitrarily build. Not our search. All right, FA. Label we use arbitrarily. Okay, so at an edge between F and A, F and E, E and G, A and G, A and B, G and B. Then we have B and C, B and D, and C and D. Good enough. So starting at vertex A. Yeah, it's good. All right, so we'll go ahead and let's draw on this. Good. No, text will be sloppy. Do some drawing. All right, so we'll start at A. Right? We start at A, so we know that A. So we'll go ahead and add our known list. We know about A. Right, so now we'll go to the first vertex. We have three options. We can go to F, F's adjacent, G's adjacent, and B's adjacent. So we're not going to be arbitrary about this. We're going to go to our first neighbor. So again, when the computer is running this, we're not looking at an image of the graph. We're looking at the matrix or the list. Based on the matrix or the list, we'll decide where to go. The first entry, that's my numbers. Back. First entry that we'll go to is the first one that shows up in the adjacency list or matrix, whichever we're using. So we're going to go ahead and go to A, from A to B rather. We're going to go from A to B. And we can go ahead and just draw that we know it. That's a known vertex. I can get back in my text box here. I guess not. Hello. And we know about B now. F and G can't be the first neighbor because they're not in the corresponding list, right? Let's go ahead and build up. Control Z is not doing what I want to do. All right, let's see, what can we do to draw out, what is this, table? Yeah, it's definitely not a table. What are my drawing options here? Ratios, okay. Let's build out our matrix. There's quite a few points. Let's see if that's enough. How many do we have? 4, 7. It's too big. It's fine. E, F, G. There's row and column. Next row and column. And so this is our adjacency matrix. A connects to 3, connects to B, F, and G. Right. So when we're at A and we see who can I go to that I don't know about, go to this row in the data set. See, as I cannot connect to A, I can connect to B, and I don't know who it is. That's who I connect to. So we come back to A later from backtracking and we look to see who we get to. We start at the beginning. I can't get connect to A. I've already been to B. I can't get to C, D, or E. But if F is unvisited at that point, we'll go ahead and go to F at that point. All right, so B connects to A, C, D, and G. C just has B, D. Oops, you're on the wrong key. Fix that. C had B and D. D has B and C. Where's E? E is F and G. F has A and E. And G has A, B, E. A, B, and E. And so let's get off to the side as we work through this. All right. Children annotations. We'll clear those. Get that fixed. All right. We started A and we went to B. And let's zero back in there and we'll save this off. Yeah. Remember, this algorithm is running off of the underlying tables. Okay, so let's grab that down here. Step 1 from A to B. All right, so now we're at B. B has 3 choices, C, D, and G, just like before. We go to the underlying table, right? We see A as an option, but we already know about A, so we're not going to go there. So our next option is C. We can go ahead and go to C from B. Oops. Wrong shortcut keys. We get selected and grab step 2 from B to C. All right, so let's keep on rolling through. Let's see, what if our vertices are named differently? Yeah, so if we were to rename these vertices, the path that the graph would go through would be different. All right, so if B were over here, it would go to B over here. Yep, so our not nearest neighbor, our first neighbor. All right, so if we have 3 neighbors, they're neighbors 1, 2, and 3. So one of them is the first neighbor. And the first neighbor is just whoever shows up in the list or row of our table. Okay, so now we're at C. So come over, look at C's table, put our options. Right, in fact, let me do, right, that one we stamped out because that was not an option. We're not going to go to B from C because we've already been there. So that goes ahead and gives us D is our one and only option from C. Go ahead and jump from C to D. As our third step. Step 3 from C to D. And now we've found ourselves into a backtrack. All right, so go ahead and jump over to D. Can't go to B because we already know about it. In fact, I haven't been updating my known vertices, so I need to get back to doing that. Can't go to C because I already know about that. And there are no other neighbors for D. Now we're going to have to backtrack. So let's backtrack. Backtrack will be green. Let's go back to who called us. Go back to C. Look through C. Right. We completed D. Now we're looking to see if there are any more entries in this row. There aren't. So it's also going to have to backtrack to B. Right. So B is where we left off, and now we continue looking to see who else we can go to. Right. We see that we can go to D, but we already know about it. So we'll just go ahead and move along to G. Right, so screen there. Enough. Ooh, can't move that. All right. So now we get to go on over to G. Try that again. Go on over to G from B. All right, B to G after backtracking. And so you see a question, if the vertices are named differently, 1, 2, 3, 4, 6. Yeah, so it's we sort, right? So just like we had the lab last week, you had the option of sorting. I just wasn't enforcing that as a requirement of the lab. But once talking about more fuller implementation, that would hold on as true. We keep it ordered. Okay. Presently, we're at G. All right, so go back to our table here. In fact, my known vertices died. Okay. Well, I guess you need to do this text box. That's probably the way to go. Let's not do that. Okay. Okay, known vertices. So here's where we started. We went to B, went to C, went to D, and we went to G. All right, so presently we're at G. G wants to see where we can go. And it says, all right, A is an option, but we already know about it. E is an option, already know about it. And that brings us over and over to E. Go ahead and transition over to E from G. And go to sleep, screenshot. Where are we in 5? Step 5. From G to E. Back up. Okay. So we are now on, for text East, we're looking at E's row. And our first neighbor is F. And we don't know about F. Go ahead and go to F from E. And update our screenshots. All right, step 6 from E to F. Now, if we're counting, we'll see that we're done. If we're not counting, we'll go ahead and backtrack. See if there are other paths yet traveled. All right, so we'll roll on back. We came, right? Because when we come look here at F says, all right, F says I have nowhere to go. We already know about A, we already know about E. No other options for F, so we have to go ahead and turn around. So we'll go back in. Back the way we came, back the way we came. Again, looking at the tables and seeing that there is nowhere to go, we get to A. Okay, A went to B to start, and then says we don't need to go R, F, or G because we've already been there. There's nothing to worry about. The question is, so the depth is 8. The longest path we created before we backtracked was 3. Right, so we went A to B to C to D, so we created a path of 3 before we had to backtrack. And then we went A, B, G, E, F, so it was a path of 4 before we had to backtrack. All right, let me go ahead and paste that and talk about the paths created. Right, so our paths created, we had A, B, C, D, and then A, B, C, G, E, F. C should not be in there. That. A, B, G, F. Right. Trying. Right, so that will be path length of 3 and, well, 3 hops, 4 vertices. Path length of 5. Check, I got my numbering there. Questions at the moment? You know, the orange arrows are just indicating the road we took. Right, so we had one road. And then we took here before we hit our dead end, and then we had another road here that we took looking around for all our fun vertices. Yeah, so I mean the depths of paths were the longest hops that we're making. Okay. With the breadth first search, we'll be staying as close as we can to the starting vertex. All those vertices that are one hop away, we process first. Then those that are 2 away, etc. This is handled by using a queue to track unvisited vertices. The algorithm is to grab a vertex, NQ, the unknown vertices, then DQ, next vertex, go to, and repeat process. Let's see. Go ahead and like this. And probably big enough. All right, so A goes on the queue to start, or whoever our starting vertex is. Where we're starting is a given, so it's arbitrary. We might have to be starting at B or D or E. Just like before, A will NQ its neighbors that are presently unknown. So B, F, and G are all unknown vertices. So we'll go ahead and NQ them. We have B, F, and G, and it's in alphabetical order because that's how we're storing the data in the graph. Excuse me. All right, so we know that we can go to B, we know that we can go to F, we know that we can go to G. All right, so we'll go ahead and flag those as known. All right, so we know about all these vertices. Once we know about them, we don't want to enqueue them again because that's just redundant work. They won't give us anything that we won't know about previously. All right, so DQ, right, predefined operation, we go ahead and DQ B. Pull that node from our queue. And that's the path that we're going to take. We go to B and we'll look and see at who its neighbors are. We'll come back and see who the neighbors are. A is already known, so we're not going to enqueue that. C is not known, so that will be enqueued, and D is not known, so that will also be enqueued. All right, so we'll enqueue these. C and D. C and D become enqueued. Go ahead and flag those as known. Orange arrows. Cheat. paths that we can take. All right, and finish processing B, so we'll go ahead and go back to the queue. We have F on the queue. Go ahead and pull that out. All right, so we're going to hop on over to the completely other side of the graph. We're jumping over to F. And we're seeing who F knows about that we didn't already know about. All right, so we have F knows about A, but we already know about that, but we don't know about E, so we can go ahead and include E by pushing that, rather than queuing it. So we know that's a path we may take in the future. All right. So let's go ahead and mark E is something that we know about. So at this point, we do know about all the vertices. Graph, so there will be no one else to be enqueued at this point. Just a matter of dequeuing. All right, so DQG. All right, not much to do here. Grab the screen. And repeat the process, right? So we'll go to G in the table. We already know about A, we already know about B, we already know about E, so there's nothing to go ahead and enqueue. And the story is just going to repeat itself. Start processing C. C says, we already know about B and D, so there's nothing else to do here. And we can get to D and rinse and repeat. All right, go to D's table. We know about B and C already, so nothing we want to bother in queuing. D goes away. You know, I just remember I forgot to draw my green arrows here. That's where we're going to. Fix my annotations and redraw those. Okay. We'll fix that at the end. And E comes along, Q gets to a nice empty state. And no new information to be found here. And let's see. Got the X out of G earlier. Drawings are all correct. That drawing is all correct. It needs to be corrected still. All right. So let's see. Right. A was where we started, we flagged it, and then we enqueued its neighbors and then flagged those. Then we went from A to B. He told us about C and D, we flagged those. Right, we jumped to F. F told us about E, so we flagged those. And next up we had G. So let's see, how can I edit this? Let's just try. Draw right on top of it. And you're just gonna see how messed up that gets. Getting a little bit of artifacting going in there, but seems to be working. All right, then we had G. Try back in there. All right, so we had G, and B was up. Was the first up in line for our NQing, so that had NQ'd C. That's where we went to next. Then after that, D was next up in the queue, so that's where we flowed to at that point. And I seem to have lost the drawings. Another one. D. Okay. Did I lose? No, we did that further. Okay. Then we got D. All right. A little bit extra arrows here. All right. And we got the F. Neat. All right, so our order of output. Output, which is generated as we DQ. And A, B, moves up A, B, F, and G. Control 0A, and C, D, and E. C, D, and E. Anybody? 1, 2, 3, 4, 5, 6, 7, and we have 7. A is at 0A as our starting index. Starting vertex, rather. E, F, and G are all one hop away from A, and then C, D, and E are all 2 hops away from A. All right, so we can go back and cross check. Look at our paths. All right, 1 hop. Let's try it again. Color. All right, B is 1 hop, G is 1 hop, and F are 1 hop. And we get to C is 2 hops, D is 2 hops, and E is 2 hops. Of these 2 algorithms, the depth first search algorithm tends to be the foundation that we use more often for cycle detection. All right, so if we're looking to see, can I create a cycle from A back to ourselves, we could do a depth first search, right? So we can go ahead and start hopping along back dead end to get to G and say, ah, there's a cycle. We have a cycle. We may have a larger cycle. There's a way to create a cycle, and right, if we're trying to build a tree from this graph, we're not going to be happy with that cycle.
You get your.
Okay, let's see. Have our graph list up next. So same thing as just like the adjacency matrix, adjacency list. So you can take a lot of your code from the adjacency matrix, bring it over here, go grab your singly linked list or your sorted singly linked list code from one of the earlier labs, grab that and then inject that into this code base. The IO for the lab is pretty much the same as the previous lab. Only difference is the underlying data structure that we're using to encode it. Let's remember our graph list is an array of linked lists. So you go get your sorted list class. Drop down here, create an array of those. It's just a matter of doing the inserts. As they add in the vertices or add in the edges between the vertices, just go to the appropriate list or lists and inject them. So code is certainly a little more complex for a simple graph here because you need to go into two lists and then do a sorted insert of a node, whereas the matrix is just an actual line, just flipping our two indices. Does this exercise make sense? Go ahead and take a 5-minute break. And then we'll work on this exercise for 10 minutes, lab time. Yeah, 7:30, we'll get back to lecturing. Any questions? As we pause the recording for now, avoid some dead air. For the weight, is that a 0 or a 1? No, the weights are just being weight of yes. Yeah, so 5 minutes break and 10 minutes lab time. Right, so it's just doing a weighted graph. So they say it's the weight's 5, 7. Well, it's just going to be an int. Okay. Mute, ping me in the chat. You have any questions? All right. Hopefully we made a step or two in the right direction with that lab, and or got a nice long break. Yeah, so we can go ahead and go over the practice test right now, get that out of the way. Okay, let's see what we have here. Build a 2-3 tree. Everyone's favorite tree. All right, so our first state, we have 27 in the tree. And we go ahead and add 49. 19 comes along, makes 27 the root. And we have our tree. So here, 24 is up next, plus the 27, so that's the first tree, 39. Pushes 49 over. Is 2-3 tree is like a binary search, but it's not a binary search tree. All right, 71 comes along, 49 is going to move over. I mean, move up. Go over next to 49. Or 27, 49, and 71 off the side here, 39 in the middle, and our 1924 node. That was 88 comes along. Goes to our third branch, and then 45 finds its way into the middle branch. Okay, values on the root, 27, 49. 27, 49. Any questions about the tree before I blow away my annotations? Suppose I can grab it. View section. Okay, on top of we? To program 2. All right, let's do. Three. Just 3. Okay. Navial tree. Who's the first node to become alpha? All right. So 60. Again, 35 is our root. 29 goes off to the right. 22 goes off to the left. So no alpha just yet. 27 is up next. Alpha, 64. Still no alpha, and then 41 pops up. All right, so the tree never becomes unbalanced. It should be none of them. Binary search tree. And which values are on the third level? Okay. All right, 69. No. Got the wrong numbers here. All right, 48 is the root. 55 jumps to the right. 42 jumps to the left. 37 goes left twice. 69 goes right twice. 19 goes all the way to the left. 31, way down there. 88, flies all the way to the right. And 53. Right, third level. So first level, we have the root. Second level, we have these two values, and then the values that we want. 37, 53, and 69. 37, 53, and 69. Question, let's see what that is. Well, this is an unbalanced tree, but a binary search tree has no restrictions about it being balanced. And repeated values would just lead to imbalance. Oh, because there's not repeated values. Yeah, well, whether there are repeated values or not, the tree can still become unbalanced. Well, it's the first level. Whether you label it as level 0 or level 1, it's the first level in the tree. Right, so right, there's the two numbering conventions, level 0, level 1, level 2, but the first is whatever you label it. You can label it levels A, B, and C if you wanted to, right? Alpha, omega, alpha, beta, gamma, omega, whatever, right? So the numbering system is arbitrary, but the first is the first, whichever the numbering system is. So I put this comment here so we have a consistency. Delete option on our min heap. So let's build the heap from here. 4, 5, 7, 9, 6, 7, 8. Let's remember, delete is always killing the root value. And then 8 falls off and wants to try to become the root, but that's not going to happen. 5 moves up, and then 6 moves up. So we'll have 5 in the root, 6 and 7 as its children. 9, 8 found its home over there, and 7. So 5, 6, 7, 9, 8, 7. 5, 6, 7, 9, 8, 7 is our tree. Okay, number 5, build a max heap. All right, 17, 17, 12, 24 is going to push 17 down. All right, 28 is going to go, try to go here, but it's going to move its way up. 24 goes down, 17 stays where it was. And 12 takes that spot, 23. 21. We have 5. Next step is 20. 20 moves up, pushes 12 down. 18. 22 stays where it is, as does 6. What are we asking for again? Values in the 4th level, right? So whereas first, second, third, fourth is 12, 18, 22, and 6. 12, 18, 22, and 6. All right. In order traversal. Let's draw the tree out. 44, 31, 69. Then we have the dead branch. 41. Dead branch and 75. In order traversal. All right, so start the root, go left, left, and where to go. So we get 31 out first. So what's first output? So first output 31. So anything else from that point? And let's see what's going on with the key. Make sure that's always good. 5 out of 6 points. That's not good. What did I goof up on? Where's my answer wrong? 3. Oh, so I wanted to wait. 3. Oh, I wanted to. All right, hold on a second. What position is the root in the output? Okay, I misread my own question. So let's go back. Stopped too soon. So 31, 41, 44. There we go. Third position for our tree. Let's read the output. I read what's the first output? And the question was super helpful to read the question correctly. Any questions about the practice test or any questions on the test? It's going to be consistent like it was the two tests. We're in the neighborhood 2025. No, test is going to be around 20 to 25 questions. Just like the previous tests. Or somewhere in that neighborhood, could go under below that range, but 20 to 25 questions on the test is the typical range. Unless there are questions that are particularly time consuming, or a lot of them are time consuming, then the number of questions goes down. Right, because O notation questions, multiple choice, those are 1-minute questions, but to build a binary search tree with 10 nodes, right, and that's like a 3-minute question. I say build an AVL tree with 10 nodes, that becomes a much longer question because there's a lot more work to do to build that kind of tree. Question 4, why did 8 move? Question 4, because 8 is the rightmost value in the heap. And after we delete a node from the heap, that position in the tree is no longer valid, so it needs to find a new home. And we deleted 4, because we always do it from root, it creates a void at the top. It's the min heap, the smaller value moves up, so we create a new void here, which was between 8, 6, and 9. The smaller value moved up, creates a void here, and there's no one underneath it, so the value that got pruned off shifts over to this point. I'll work on that one later. All right. Let's see here. More terminology, make sure we're on the same page. 4.5 graph path. And Wikipedia up here. And let's see what we go for. All right, path. Let's see, is it one else? What kind of path I want? Graph theory. There we go. Right, so you can see walk, trail, and path are all synonymous here, but basically it's a sequence of edges, and edges are defined by pairs of vertices that goes from a vertex to another vertex. And there can be multiple paths between. Oops. Right, so path sequence of vertices in the graph. Right, so let's go ahead and create a graph. Trying to create a graph. Grab my shapes here. All right. And keep the graph nice and small. 4 vertices, A, B, C, and D. And we'll put an edge between A and B, A and D, A and C, C and D, and B and C. All right, so some paths in our graph here. And we got a path AB, ABC, and ABCA, et cetera, et cetera. And excuse me, ABCA. Lots of paths that we can grade. No. The circuit. Let's see. Cycles. Right. So here, terminology in circles and cycles and circuits can be a little bit overlapping. All right, so in the above past examples, as A and maybe CA are cycles. Where all the vertices are unique for the starting and ending vertex. All right, so if we were to extract those paths, ADCA, let's heads here, ADCA, that was the path that we took. All right, you can see that's the cycle graph, that's the C3. ABCA, same story. There's a subgraph that we are creating here. Is a cycle graph, so that path is a cycle. Order. A to B, B to C, and C back to where we began. Right, so when you have a cycle, could start on any of the vertices on that cycle and create a path back to yourself. All right, so circuit here now. All right, so this probably good part of Wikipedia to keep over here to differentiate, and this being the important line. All right, so a cycle is a circuit, specifically a simple circuit. All right, so we can create, go back to our original graph, and roll around our paths. A, D, C, A, B, C, A. All right, so we started and ended at A, but we have repetition of vertices inside the path, even including A. All right, so basically more or less a composition of cycles in the graph. Now, where we're going to extend this is to Eulerian graphs. So the characteristic, the graph being Eulerian, when we can create a path that traverses every single edge in the graph without repeating any of the edges. Create a path. If we stop where we started in the path is an Eulerian circuit. If we don't stop where we started, then it's an Eulerian trail. And as a cellular trail path block, synonymous. A related area is a Hamiltonian graph. A graph that is Hamiltonian will have a path that covers every single vertex exactly one time. If we stop and start at the same vertex, that path is a Hamiltonian circuit. A cycle, in this case, is repeating the vertices. Otherwise, same as before, it's trail. A Hamiltonian trail. All right, so determining the graph contains a path that meets Eulerian or Hamiltonian. Hamiltonian. Can be determined. Oh, all right, so for Eulerian, we need the degree of every vertex in the graph to be even. Were there to exist in Eulerian, we have two vertices have an odd degree, and all others are even, and we have a trail. Right, yeah, Hamiltonian, because the circular cycle, the first and the last are the same thing, because you beginning and the end. Hamiltonian graphs fall into the category of NP complete mean. It is very difficult to find out if such a graph exists. However, if the graph shaped graph, then we can be deterministic on finding such graph. And NP right, so non-deterministic polynomial time, which means basically, remember our O notations. We're looking over on the factorial side of the charts. For how long these things can take. We'll get into some areas of application of these, but first let's go ahead and do some Euler, do some sample graphs, and see what characteristics. Yeah. Okay, let's do the one you might be familiar with already. It's a puzzle you may have done when you were younger. It challenges you to draw a house. You need to draw the house in such a way that you do not lift up your writing implement. Remember, the house is a square box with a roof and cross over at the diagonal. Right, so you always just brute force it, start somewhere, start drawing, see if you can make a pass such that you cover every edge. And I failed here. If I had started here and then gone that way, still would have failed because I still have these two edges that are giving me problems. But with Euler, we have information that we want to make sure to see if even such a thing exists. The degree of our top vertex is 2. Our roof line here, we have degrees of 4. Then at our foundation, we have degrees of 3. And so these are our key points. Right, so when we have the top vertex, there's a road in and there's a road out. Right, so one in, one out, when we get to that point, means our number of edges that are still incident with this vertex drops to 0, which means we've consumed all the edges from that vertex. Same thing is true for our 4 vertices. For every road in, there's a road out. Whatever the road was that we took to get into a vertex, when it's even, that means we have a road in, road out. So first time we went through, we took it from 4 to 2, so we still had way in and way out, and then we take it down to 0. The next time that we run through that particular vertex. So when solving or trying to find what one of those paths are, at this point, yes, an Eulerian characteristic exists here. And because there are 2 vertices of an odd degree, it's only going to be a trail. And the only way for us to have that trail exist means we're going to have to start at one of the 3s and end at the other 3. Because when we go make a road through here at one point in time, that means there's going to be one left, which means that we have to start there. So if we start at this 3, for example, then we're down to 2 roads still connecting with that vertex. Right, so there's lots of ways we can go. Let's do a first one as red. And let's go along the top, down over the side, and there is a path that we could have taken. And go orange, start over here, bounce around across, down over there, down the side, and we get orange everywhere we go. So if we start on 1, 3, we'll end on the other 3. Lots of ways. See that this is Eulerian or not. And so here's our Eulerian. Trails, be many of them. All right, so for Hamilton, if the graph is small enough, I jumped ahead. When I said Hamilton's NP complete, finding the best one's NP complete, which is our traveling salesman, like finding if there's a path that's Hamiltonian, right? Basically, if you can see if there's a cycle in the graph, then you're good to go. All you gotta do is hop around. And the fact that we didn't use these edges, we don't care. Hamiltonian doesn't care about edges. Only cares about the vertices. Can we hit every vertex and get to where we want? And since there's a lot of different edges here available to us, we just have to be careful on the road that we take. Okay, so if we were to try to take this road where we started here and then did a little zigzag, we ran into a little problem because this particular path would start over here. It's just a trail because we couldn't get back to where we started. So we do have to be a little bit careful on our choices because there are going to be things called cut vertices and cut edges where we can start disconnecting the graph and isolate some sections. So programmatically, this gets very complicated very quickly. But if there's a cycle, then that becomes easy enough to find. Let's see. Now we'll go ahead and roll over. Let's see. Hamiltonian assumes the same thing about the start and end. At the start and end, so if there is a circuit, you can start anywhere because it's a full circuit. You cycle all the way back to yourself, it means you can start anywhere and you just follow the same road. The trick is when there's forks on the road, which fork to take. And it's basically stay around the perimeter type as a strategy to circle around and then work your way. So the more complex the graph is, the crazier it gets. The algorithms are going to be a little bit beyond what we're going to try to do. But if you're regularly shaped graphs, Right, so like a cyclograph, for example, the degree of every vertex is 2. Thus, we have an Eulerian circuit. Right, and if you say that you have an Eulerian circuit, an Eulerian trail is irrelevant because you already have a more restricted type. Right, and say I have a football in my hand. A football in my hand, I don't have to go ahead and say I have a ball in my hand because it's already there because I have a more specific qualification on the type of ball it is. Right, and cyclographs also Hamiltonian. Start where you want and just roll around the edge and back where you started to create the circuit. Says my internet connection is unstable. How well is the audio coming through at the moment?
It sounds okay.
All right. We'll carry on then. Star graph. Right, so the degree of every vertex here is 1, save the middle. So unless we get trivial with an S3 is a straight line, 2 with a degree, and 1 given degree, which is an Eulerian trail. We're not going to get far. Using with S2, 2 vertices connected together, 2 with a degree, everyone else is even, everyone else being the null set. Why do we want to know if there's one in the circuit or not? Second, why? We have to get back to you with that because I'm spacing at the moment. And why do we care? A whole lot of oil and circuits, the goes to the bridges of Königsberg, like 15th century like that. We're ask the question now, so let's go and bring it. See if I can type correctly. Bridges of Königsberg. 18th century. My time's confused here. And so way back in 1736. Another history lesson here. There's these bridges connecting the various land masses about this river. Where is this again? I forget where it is. Somewhere, Prussia. And there was a competition among scholars, nobles, or whatever it was, or so the story goes, to see if they could make a thing from somewhere such that they cross every bridge and then get back without repeating the bridges, right? We started here, we cross those bridges, As soon as we get back here, we're stuck because we've taken all the bridges that leave here. When we go here, same thing, we cannot get back. So Euler came along and mathematically, again, winking at us, mathematically solved the issue. I made this landmass a vertex, got 3 edges coming out of it. This landmass, the vertex, we have 3 edges coming out of it. Same thing here, landmass, 3, and then an LMS of 5. They all have an odd degree. And so being able to find paths that can traverse. So I believe circuit theory or circuit design blends in that as well, but otherwise, I'm hugely interesting in computer science. Hamiltonian is traveling salesman problem. We'll get to that one later. There's star graph, wheel graph. Wheel graph, right? The degree of every vertex is 3. So unless you want to say a W3 exists, which no, because there's no center point, right? So W4 and up, everyone's got an odd degree. So we're out of luck finding any Eulerian characteristics. Hamiltonian, however, sees that there is a cycle around the graph. All we need to do is jump into the middle, some point, and jump back out to create a circuit. And so let's create a wheel graph. And create our cycle around the edge. And then connect up the middle. All right, so we can go ahead and create a path. Here, easy enough. Highlighting. Okay, let's try it again. Take a path, consume vertices at some point, jump in the middle. Doesn't really matter when. We can go ahead and get back to where we started. Without any trouble. The fact that there's a cycle in the graph makes it easy for Hamiltonian graphs yeah, interesting. Hidden line here somewhere. Anyways, good enough. Capture, so leave it. So no problems with wheel graph, Hamiltonian. Bipartite graph, we're not going to really bother with. Complete graphs. Euler is a sometime proposition. Graphs where the degree, all the edges, or vertices rather. Meets the criteria. And Hamiltonian. Falls into the always category. As we can get to intersect from any other vertex. Traverse the graph and create the circuit. long as the laptop is chosen to be to where we started. Complete bipartite. Bipartite. This is going to be an exercise for you to digest and figure out which, if any, would have one or more of these characteristics. Remember, the degree of a vertex in complete bipartite is driven by the set size, the opposite. That's if you have a K23, you have 3 vertices with an even degree of 2, and you have 2 vertices with a degree of 3. So you'll certainly find some of these in ones that you build up. So the logic analysis that needs to be done there. Okay, let's go ahead and take a 5-minute break. And we will carry on. Good old Wikipedia. And right. Fixing notes over there. So traveling salesperson. Right, so the objective of this problem is given a set of vertices. Find a path, Hamiltonian path, that is the shortest Hamiltonian path amongst all paths available. All right, so make this fully abstract. We take a K5 graph where we can get from anywhere to anywhere we want. Number of paths here is fairly high to start. All right, so say we start at vertex 0. There are 4 options to choose from. From any of those, there are 3 options to choose from, and 2, etc., more n factorial. Of course, that does include mirror paths. So just with a 5 vertex graph, or 5 factorial, what? 20, 60, 120. 120 paths to choose from. All right, quite a few. So the objective to find this amongst, so to find the best solution in a fairly small problem set. And take a computer. More time than it has, or it would burn out of old age. Right, so there are suboptimal solutions. Where we can find an answer that is close to the optimal solution, but can find the solution in a reasonable amount of time. And there's triangle inequality, what's it called? Spacing on it. Try to anyway, we will look at one way when we start working on minimum spanning trees, or wait till we get to that in a second. Oh yeah, we're not going to get into the fine details of the algorithms to solve traveling salesman. It's just a concrete example that we use for our Hamiltonian graphs. Right? The why behind why we're bothering to talk about this, right? Because it's going to be composition of our data structures, and then there are various algorithms for which we might employ to solve this particular problem. All right. Before I start spinning into another topic, are there any test 3 questions, right? All trees, trees, and more trees. And of course, O notation is ever present amongst pretty much all the tests we'll take. On the thread of questions, let's talk about program 3. See how we're doing here, see where we might be stuck. Right, so names and weights are our 2 data points, just like with program 2. It represents person. Everyone's good for number 1. Right, 8 people submitted already. That's good. So we can get 8 people a day. So now it's a Saturday, we'll have almost everyone covered up. Might need to have a little bit of an increasing trend on that one. I assume we're good with the traversals. These are 3 of the easier parts. Right, just draw the tree out on paper, do the traversal on paper, and then feed that tree into your program and validate that it produces the same result as you did on paper, and then you know you're good. Question is, if the test is all multiple choice, or an answers only, or the programming code. There's always potential for writing code on tests, right? Tree building, tree traversals, all that fun stuff can find its way onto the test. Right, finding the height and the number of leaves. These are going to be recursive methods, right, where you need to ask each subtree, your left and right subtrees, how tall they are in the case of height, or how many leaves they have in the case of leaves. Right, so for height, and if we draw out the tree, right, so the root of your tree, you're asking it how tall it is, it has to go ahead and ask how tall the left subtree is, how tall the right subtree is. They in turn will do the same thing. They're going to ask the same question of their subtree. How tall is my left subtree and how tall is my right subtree of this leaf, right? So comes back and says -1, comes back and says -1, right? That's your base case. Is when you get to an empty subtree. -1 is returned up, -1 is returned up. Take the max of these 2 numbers. -1, -1, -1, and then add 1 for yourself. And this tree is reporting back that its height is 0. Okay, so we're making the same questions over here. Get to a leaf node, and it returns back I in the 0. Get to our node here, called our X node. Do the 0 on one side, -1 on the other. Takes the max of those 2, 0, returns back to 1. This side saying I'm the height of 1. Same here, 0 and 1. And it says the height of my tree is a 2, right? Length of our longest path, 2 hops. And coding wise, changing this pattern to the other pattern being 0 height for empty trees as opposed to -1. It's just your base case. Instead of returning -1, you return 0, and then that's it. Right? Trivial and arbitrary to a certain extent which way we go there. same idea with leaves, slightly different math, right? So we ask subtrees how many leaves there are. We know we are a leaf when we have 2 null pointers. It says back, I have 1 leaf. I am a leaf. So we return back 1 leaf on this side. Comes in here, I'm not a leaf, so I'll ask my children. Says I'm a leaf, return back a 1. Says I'm a leaf, return back a 1. And you just add those together. There are 2 leaves in this subtree. That 2 comes back with this 1. Right, add those together and we get 3 leaves in the entire tree. This is just for Crystal algorithm. Just need to go from your base case and make sure to start with a single node tree or an empty tree, whichever you prefer. And build up from there. So that start small. When you build a tree, starting small is key to getting the code to line up. Right, search, that's just basic functionality of the binary search tree. And the lowest weight in the tree, this one's going to be traversal. Right, because there's no order on weight. Weight does not have orders. So basically, ask the left side, who's your smallest? Ask the right side, who's your smallest? And then take the minimum of those. And the first name in alphabetical order, this is just a structural question. Since we are keyed off of names, there is by definition only one place where the lowest name in alphabetical order will exist. Just need to go dig to it and you're good to go. Right. Again, like before, don't worry about the exe if you're on a Mac, whatever. But you need the source code, of course, sample output. And then you can drop your code into my test engine and make sure it's giving correct output or not. Right, you can read the data from the screen. Just as a reminder, online compilers or input can be text-based. You just type in the numbers. 15, Tina, 24, because you're doing in decagrams or whatever here. Same thing if you're using Visual Studio, you can redirect from a code file via DOS. Or you can hard code it when you're testing and just through the hard coding and move your CN statements. Any questions about program 3? Such a chatty class tonight. We're all victims of it being Monday, aren't we? Okay, how much time we have? Done 10 minutes left, done 10 minutes break. We have an hour and 15 minutes. We'll have 30 minutes break, so 45 minutes. Okay, let's point out what we're going to be talking about next. Range for path. See if this gives me dexters or not. Here we are. What? Let's go ahead and put some links in here. For where we'll be hitting next time. So effectively, maybe switch for like that. Yeah. 2 a.m. That's what the problem was. That's what I want. I'm just looking at my algorithms use that one for pairs, other shortest path, which is all pairs shortest path. Nice consistent plots here. All right, so you can check these out. In fact, I think I owe some more readings at this point, don't I? Are we? Yeah, okay, I need to add some more sections here. I don't know what happens when I'll start adding some graph sections there in the reading. And I'll make a reading post later tonight. So we can follow up in the book while we're doing that. Otherwise, at this point, we'll just talk about our graphing code. We'll go over graph matrix again. Some people still have to turn that in, and then we'll talk about our adjacency lists. And we'll be using C# just that much faster for me to do it in C# than it is in C++. Yeah. We'll go ahead and do the list first.
Back we go.
Because, 1 second. And then we hit, so we'll start there and then we'll move on. All right, so this one was built off of our only linked list, so we'll need to have things probably. I'll try to be more analogous. Let's see. All right, so we're recreating two that we've done in the past. Nice node. Our head node and add function, right? So like before. First case you always want to consider is the list empty, because that's your guaranteed starting point, is starting with an empty list. Then we go ahead to constructor. See, does that work? Here's personalized and not do that. Right, list nodes, naming good. Otherwise, we need to find where to go. One of the other ways of adding to a single linked list we haven't talked about before is by just attaching the node to the list and then just doing a sequence of shifts to get the attachment in place, right? So see if I can remember what logic is for that one. So at this point, right, so I have a couple of scenarios. Let's draw it out. So we say we have 10 that came along the first time, and that became our list, and it points nowhere. Then we have 5 come along. All right, so in this circumstance, the node is pointing to it. It's already where it needs to be. And we're good to go. Well, let me just do the check. If No data. Data. Then head data. And we're done. Otherwise, I'm going to do some shifting. So if we have a different scenario, so that's our list. Then we want to add in, let's say 7. So right now we have 7 pointing to 5, pointing to 10. So what we need to do here is shift it over. And I should have done some research before I got here because I don't remember the syntax for doing this. Let's think. I'm going to need a temporary pointer. So no temp equals head. And right now we have node right here, and node is pointing to temp. Go ahead and have node next equals temp next. Do that, that forms a bridge. Now we just need to have temp follow along. Temp next. Oh, temp null. And let's see, where are we in relationship here? All right, I'm going to circle back to this because my brain is feeling a little bit befuddled on this one. Temp next, data, less than no data. Okay, thank you. Let's see. Wow. Temp next, data, less than no data. Yeah, clearly I don't want to think tonight. And at some point, I believe we still need to bridge the predecessor. And then our add will be done. So I'm pretty sure I have a bug in there, and we'll fix that in a minute. Let's graph this part. All right, so public link list. Where list? Right, so a constructor, if I can type public. See how big this is going to be. And we have that. Public void add, take some data. Right, and the other thing we need to do is label. It's based on where our label is. Add that into our list. String array for labels, just like we did with the matrix. We just need to find where that label is. In our labels, get our index, and then we can go ahead and just add Where data? All right, what do I call it? But it's not like public. There's there, linked list. Okay. Now, just delete it quickly. All right, and that adds it in. And so next up, we need to print for each linked list. Hello, the print, which we don't have just yet. Get that. Okay, print function. And this node, temp equals head. And just spit things out. So we don't have to test for empty things. So the key thing is, label along here. So no. Add that. Zero. Less than count blank property plus, and we'll do this I to print it, passing along labels I. Right, while temp equals null. Go ahead and print out. And we are going from our label to wherever our temp node is spitting out. One of the things I forgot to do here was let my label information be known down in my list node. So I want to add that in here so I can actually print out the labels, or now it's just printing out the data points. And of course, there's the bug in my add method because I don't normally use this approach, so I don't code for it. So I've forgotten what my syntax needs to be. I'm pretty sure this is pretty broken. And first very low key prompt, however big it is. This size, and then all that fun stuff for actually adding things. But go ahead and validate how broken this is really quickly. Let's say 5. And I got no reference. I had a feeling I was adding some $1 trillion mistakes somewhere in here. The list. Yeah, saying is no, and the labels are saying is no. That's interesting. Line 66. Oh, this is where we want to use Visual Studio so I can step in and see where my null references are. Clearly something's broken. I have a typo somewhere in here. I just can't see it off the top of my head. I didn't initialize each list itself. That's my problem. Plus this is I equals new. I should figure out null reference at least. Has no orphans are bad, and it doesn't turn anything up because nothing in there. Everyone's still with me here, aside from my bugs. All right, need to add in some code. Call our add method function so that we can start creating some edges. Inside our graph list. So there's our buggy code. Just want to refer back to it. Questions at the moment? Okay. Is there an index of equivalent? Maybe like find. They're ordered, so you use quicksort. Index of, yeah, there's, let's see what it is. Like standard. Yeah, that's a nice clean example. Yeah, but I just linear search there. There's gotta be something in here, right? No, everyone's writing their own function. I love C++. All right, they are sorted, so you can use quicksort. All right. Their built-in types should be good. You might have to write a compare. It's kind of annoying, but right, use word to find the values and return back the index of the values. Yeah, you can easily write linear search, but you just take your lab code, right? We did linear search way back. What was that? 8 weeks ago? 7, 8 weeks ago? Oh, wow, we're close to pretty much halfway through the course here. Losing track of the weeks. The blur becomes blurrier every time we go over something new, right? Where's my Windows? Where? All right, let me change this. Let me change to a jagged array because that would be a similar syntax to C++. Broke it. Rank specifier. See. I'm breaking my own syntax here. Okay. Oh, now I have to check my syntax. And what is my syntax here? Unbounded second size. Go. That's where I was goofing up. Okay. Size. This. Reason I do. Okay, that's good. Let's change my curve here as well. Do I have that? All right, that's tricky. This is for A, B, C, E. And since I lost my B, whatever, A and C, and whatever the empty one was. All right, so those of you who have not finished Matrix Lab, or do you want me to spend some more time on this? Yeah, I can share this again. Yeah, no problem. All right, so changing to a jagged array is a little bit more similar to the C++. All right, so these become star stars. Okay, let's translate it into C++. So enough. There. Labels. Fine. See how much you have to break here. String concatenation there, whatever. And let's do the sort. All right. You know, I was playing a quick sort earlier. I'm going to say B search or binary search. Here's where we would use the quick sort. Sort our labels. Yeah, I'll say that for. We'll just come down for a minute and add that as an enhancement request in a minute. Index. If 0 less than size plus labels 2 labels I turn I the last turn 1 into there. Index from 2 out.
Hey, you guys need to take your bath now. No, I don't want you to do that. Go.
All right, let's see what else we have here.
No computer, no TV for either of you tomorrow night.
Let's go ahead and
If you're not going to take a shower tonight, then you don't get that
my
tomorrow.
manual class. Static. Extra code here and fix our test. Is it not gonna? I forget if you try to tell me they didn't overload. Plus, if that string overloaded the plus operator. I will. If they didn't, I will fix that. Let's see. Int size. Do star label, string, matrix, new. Save.
No, it's getting up.
Dump. What else have gotten broken here? Text. One break, otherwise the next one. Text and there it is. All right. Let's see what you don't like. That's need. Oh yeah. Gotta fix my access modifiers here. Public size. And private top. Construct use that label, get right. See what bugs I have, my transformation. Too many public yeah, must be coolers. Oh, too many curly braces somewhere. Oh. Transitioning between languages is always fun. Okay. All right, let's see. 4 vertices, A, B, C, and D. Between A and B. All right, seems we have definitely some printing issues here. As was called out with my dump. Probably not. Can't make it very well, so where's my dump? Dump. We'll see how well that works. And count goes small. There we go. Dump's working a little bit better. A, B, C, A, and B. All right, and there we go. Let's see. Let's save. I think I have an account over here. There we go. Matrix. There you go. Gotta have matrix references when you're talking about the matrix, right? It's just a requirement. Otherwise, what's the point? And so a lot of the code we got to keep between the languages, right? So that's syntax changes for how we do jagged arrays in C++ versus C#, right? And the way we do public and private, just a lot of tweaking, and then C outs and C ins. It's actually a little bit easier, especially with C in, because they've overloaded the extraction operator to look at the type that you're trying to extract into and handle all the fun conversions for you. We have to manually handle that good stuff. Yes, we want to sort. Add. Can't add. Int string left right. Remember my syntax here. And just going to do string left, right. And if that doesn't work, that's what Google is for. No matching calls. New sort string. Do, 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 do. Here's my Q sort. Where's my compare function? Const char star. Really? Those are C strings though. I want to pass actual strings. I don't think that's what I'm looking for. Let's try that again. Stack Overflow. And these are char stars. Well, we'll just go ahead and leave sort off the table. Google is not. Let me just get rid of the key part. String array. Sometimes you need to ask the question differently. See if we can get what we want. There we go, standard sort. Let's see what version of online TV we have here, and sort begin labels and labels. And let's go ahead and add a print edges functions. Have some intelligence here, and we'll see what the actual labels are. So. Yeah, it's always the same code. If test, if row call 0, we can do some outputting in here. We want labels row. And I forget what the output formatting specified to be, so I'll get back to that later. It's just comments to the list, wasn't it? Zeros. That. All right. Now let's use something called print edges. See how that works. Sort, not a member of standard. Wow, this is just terrible. Mad at me because I'm saying using standard and using standard. Like that is it. I have a feeling we got a problem with version of the compiler that they're using. No match function for call again. All right. They're cheating using vectors. All right, well, again, sort falls off the table because it's not cooperating with me and I don't want to fight with the code. We'll do 3 vertices. A, B, C. Find an edge between 2 of them. And there's my list so far, A, B, add a B, C. And looks like I can give her some new lines in my outputting here. In CB. Give my extra white space. Print edges. There, and there's that one. There's the save button. I assume the share link is still good to this one. Let me know if it's not showing you the current version. Share button, see what it says. And it's actually changing the URL, so pop it out there. Of course, there's always more than one way to fry the egg, especially when you're trying to scramble it. But something along these lines, more or less good to go. Otherwise, unless there are any other questions for tonight, I do believe that will be the end. Yeah, some syntax can be cumbersome, especially with multidimensional arrays, because often a brief subject when you take C or C++, and sometimes one class assumes the other class is going to cover it, and then no one covers it. That's always fun. All right, I'll be floating around on the chat. Go ahead and stop the share, go on mute. So any other questions, go ping me in the chat or on Discord. We'll be taking the test first thing next time, as we did last time. Knock it out of the way and then carry on with our graphs.